Okay, let's get started with the last session of the afternoon. So after this talk, we'll also have our group photo. So we'll probably, when the talk is over, we'll go out to the hall outside and take it there or maybe somewhere else. But for our last talk of the day, we have Tamala Feast from the University of Sydney, who will talk about holonomy of complex projective structures on substances.
Thank you very much. And I would also like to thank the organizer for organizing such a great conference. It's my first time in Korea and really enjoying it. And also before beginning, I would like to apologize to the experts because I will be a bit boring for 10 minutes. You already know very well what I'm going to say, but hopefully you will learn something at some point. Okay, so I'm going to start by fixing a closed oriented surface of genus G that is at least 2, unless when I say that it's not. And yeah, I have even a picture so we can really think of the surface as fixed, it's not moving. And when X is a topological space and G is a subgroup of the homeomorphism of X, then a GX structure or a geometric structure on the surface is just an atlas of charts into the surface, on the surface into X with transition maps that are in G. And I will give you now some examples that I want to focus on today. So the first example, I will spend a lot of time talking about this example. It is the example where X is a plane and G is a group of translations of the plane. Then GX structure like that, I want to call it a translation structure or a translation surface structure. And an example is given as follows. You can just think of Z2 as acting on the plane. And the quotient of R2 by Z2 is, of course, a torus. So if your surface is of genus 1, you can specify a homeomorphism between the two, and you get charts into the plane with transitions that are translations. Okay. And another example that is maybe the most important one is basically the same picture, but now you replace the plane with the hyperbolic plane. So X is the upper half plane, and G is a group of orientation preserving isometries of the hyperbolic plane. So it's the group PSL2 of R. And we actually just learned about those structures. So you can basically do the same picture. If you take an appropriate lattice in PSL2 of R, then H2 modeled by this lattice will give you will give you a closed surface and you can have any genus at least 2. And if you fix an identification of your surface with the quotient, then you get charts into the hyperbolic plane whose transition will be elements of PSL2 of R. Okay, and we call that a hyperbolic structure. Okay, and the uniformization theorem also tells us that a hyperbolic structure is the same thing as a complex structure on the surface. Okay. And maybe an example that I need to mention because of the topic of this conference is the example of real projective structures. So when X is a real projective plane and G is a group SL3 of R, this is what we call a real projective structure, but this is not what I'm going to talk about. What I want to talk about is the complex projective structures. So I'm considering surface modeled on CP1, the Riemann sphere, with transitions that are Möbius transformation. So that are of the form AZ plus B over CZ plus D. And maybe just to give you motivation, this is obviously an interesting, I think you don't doubt that it's an interesting thing to look at, but maybe some extra motivation comes from the fact that the structure they appear naturally when we consider second order linear differential equations on Riemann surfaces. And also, maybe another motivation is that it generalizes the hyperbolic structure, right? Because H2 H2 is in CP1, and PSL2 of R is in PSL2 of C. Right, so it's a generalization, and it also generalizes the translation structures because C is included in CP1, and the translations are Möbius transformation. Okay. And one thing maybe a bit less classical is that I want to consider branch structures. So I want my charts on my surface to have maybe branch points. So they can be ramified, meaning that my charts are just locally conjugated to the map from the unit disk to itself. That is, Z maps to Z to the n+1. Okay? And when I have a point like that on my surface, that where n is at least 1, I call it a branch point, and n is the order of the branch. Okay? And those branch points, they are isolated, and we're on a compact surface, so you have actually a finite number of those. You can ask questions at any point also. Okay? So when we have a GX structure, a geometric structure, we get two maps. We have already encountered those maps several times, but I will still recall how that works. So if you have a geometric structure on your surface, you can look at the universal cover of your surface, S tilde, and you can define the developing map like this. What you're doing is that you're taking a very small, say, disk on your universal cover that maps to the domain of a chart downstairs. And, well, your chart maps into X. And so you define the developing map on this red disk to be the composition of those two things. And then what you can do is sort of extend your chart to some super chart, right? That is on your universal cover by just extending little by little. You take small disks that intersect your first one that are in the domain of a chart, and you make sure that they agree on their intersection, and you extend like that little by little your developing map to define it on the full universal cover. Okay, so you get a developing map from the universal cover into X, and you also get a holonomy representation from the fundamental group of your surface into G that records how your charts change when you follow a loop. Okay, so it's defined as follows. You have the developing map when you evaluate it in gamma Z, where gamma is an element of your fundamental group. It's the same thing as rho of gamma that acts on the developing map of Z. Okay, so we get this map that goes from the set of geometric structures into the set of representations. That is a very important map because it basically allows us to have sort of bridge between this very geometric world of geometric structures and this more algebraic world of representations. So it's the conjugacy classes of representation. Okay. And the question I want to address today is basically what is the image of this map when we're looking at complex projective structures. Okay. And maybe just to motivate the question, I want to recall two famous theorems, which tells us that indeed this connection is very deep. The first is the one of Goldman from the 80s that tells us that the Teschmüller space, so the space of hyperbolic structures, modulo isotopy, is exactly the same as one connected component of the space of representations. So it's a bijection onto a connected component, which is, of course, way more than just a bijection. And from the 90s, we have the same sort of result, but for a convex projective structure. So the theorem of Choi and Goldman that tells us that the convex projective structures are actually the same thing as the Hitchin components. We have a bijection between one component of the representation space and the geometric structures that are here. So I didn't define what is convex projective structure, but I think we basically all know what that is. Okay, do you have questions before I give the answer to this question? No? Okay, so so this question that I ask here has been answered in the in 2000, and the answer goes as follows. So take P of N1, Nk to be the projective structures on S, whose branch points have order N1 to Nk. Okay, and the theorem of Gallo, Kapovich, and Marden is a theorem that answered the question that was open for basically 1 century, because I mean we even have I mean Poincaré actually asks this question explicitly. So to characterize these holonomies, and the theorem goes as follows. So a representation rho is the holonomy of a projective structure if and only if it is non-elementary and it lifts to SL2. And it's the holonomy of a projective structure with a branch point of order 1 if and only if it's non-elementary and does not lift to SL2. I'm just going to define these terms now, non-elementary and lift. So as you can guess, lift means that for rho to lift, it means that you have a rho tilde that goes in SL2 of C, such that rho is the composition of rho tilde and projection. It's actually, I mean, the representation that lift form a connected component of this space of representation, and the ones that do not lift form the other connected component. And elementary means that the action of the image of rho on TP1 or on H3 has a finite orbit. Okay, so elementary is a very degenerate thing for representation. It means basically that you are either in SU2, in PSU2, or maybe you are in the affine group, right? You fix a point in CP1, so you actually act as an affine group. Or maybe you have 2 points in CP1 that you preserve, and that you preserve as a set. You can exchange them, and you act as some kind of dihedral group, maybe infinite. Okay, so I'm going to tell you what is the strategy of the proof of this theorem. Okay. So it goes as follows. You start with a representation, and you want to show that you want to geometrize it, meaning that you want to find a geometric structure whose holonomy is rho. Okay? And the first step of this proof is to find a Schottky, what I call a Schottky Pence decomposition for rho. Right? So you want to find a Pence decomposition of your surface such that when you restrict your representation to each pair of pens, you get an isomorphism onto a Schottky group. Okay, so a Schottky group is a special kind of free group in PSL2. And this is actually generic. If you take like a generic representation and you look at what's happening on a pair of pens, you get a Schottky group. So what you want to find is some kind of generic form for any given representation. Okay, so why would you do that? What is the point of this first step? well, the point of this first step is that the Schottky group on each pair of pens is easy to geometrize. It's actually not too hard from the definition of a Schottky group to find explicit charts into a CP1 such that the holonomy is your given Schottky representation. So you can find charts on each pair of pens that work exactly as you want, that give you the right holonomy. And then you have a step that is, I mean, then you have charts on each pair of pens, but they maybe do not coincide on the boundary, so you cannot really glue them. But there is a trick in on complex projective structures called grafting that allows you to basically insert cylinders that have charts on them and connect the pair of pens all together. So you can like that construct a projective structure on your surface whose holonomy is rho. Okay, so that's the proof of Gallo, Kapovich, and Marden. But unfortunately, there is a little problem in this proof, meaning that the first step is actually not entirely true. There exists representations, non-elementary representations, that do not admit this kind of decompositions. But fortunately, they are very rare. They only occur in genus 2 and are actually classified. And I will just tell you how to define them because I think it's quite fun. So I call them the pentagon representations, and they are defined as follows. So the fundamental group of a surface of genus 2 is a subgroup of index 2 of this group with 6 generators that are all of order 2 and whose product is 1. And the way to see that is to look at the hyperelliptic involution on your surface. So if you the stick and you turn it, the hyperelliptic involution, if you look at the quotient, you get a surface like that with 6 marked points. And you just look at the map induced at the level of fundamental groups, of our default fundamental groups. Okay, this gives you this inclusion as an index 2 subgroup. And now you can define the pentagon representations just as a representation defined on this bigger group by killing one of the QIs. So, and okay, that's the definition. It's just a representation defined here where you kill one of the QIs. And what you can do, for example, is take in the hyperbolic plane a right angle pentagon and define Q1 to be the order 2 rotation on this point, Q2 to be the order 2 rotation on this point, Q3, Q4, Q5, and Q6 to be 1. This gives you a non-elementary representation. And if you're bored, maybe you can think of it as an exercise to show that they don't have a Schottky pens decomposition. And the hint is that the mapping class group of a genus 2 surface basically act as braiding those QIs. And so that's a hint. So an exercise is to show that they don't have nice pens decomposition. Okay. So, right, we had a problem because we had a proof, but basically a counterexample to one of the steps. But actually, it's okay because the thing is that these counterexamples are well controlled. We understand them completely, and so we can give an ad hoc proof for those guys. So this theorem of Gallo, Kapovich, and Marden is totally fine. Because we show that those representations are holonomies of projective structure with a branch point. Okay. So this theorem is very nice, and it gives us the characterization of the holonomies of projective structures without branch point or with one branch point of order 1. And of course, the question we want ask after that is, okay, what about a general set of branching points? And that's a bit too complicated for now. I mean, I will tell you at the end, but it's a bit complicated for now. I want to look first at a simpler question, which is, okay, what about the translation surfaces? They're easier, we can do more pictures. So let's look at the translation surfaces with branch point of order n1 and k, and I denote that by h, n1, and k. And we can ask the same question. Basically, we have the holonomy that goes from this space to the representation of the fundamental group into C, right? Because now we have G is C, up to conjugacy, but C is abelian, so there's no conjugacy, which is just the first cohomology group with coefficients in C. So yeah, what is the question I want to address now is what is the image of this map? Okay. And just before answering, I want to tell you a little bit more about translation surfaces. So translation surfaces, recall, I define that as GX structures on a surface with G that is group of translation acting on the plane. But there are many ways of thinking about those objects. So a very common way is like so. If you take a polygon, like this one, and here you see that my sides, go there, see more. So my sides have colors, and what I want to do is to glue the sides that have the same color together, and I will do it just by translating them. Okay, so the blue one is glued to the blue one, the black one to the black one, and the red one to the red one. And by doing that, I will get a closed surface. And this closed surface will have a GX structure, right? Because I am in the plane and I'm gluing by translations. It's actually equivalent. So the datum of a R2 structure is the same thing as the datum of polygons with sides identified by translation. So that's a nice way of defining those. And another way of thinking about those objects is as follows. So since you have charts in the plane, you actually get a complex structure on your surface. And you have also the form dz that is invariant by translation. So you get a holomorphic one form on your Riemann surface. And actually, there's a third way of thinking about translation surface. It's that it's just a couple of a complex structure and a holomorphic one. Right? So we can think about the space of translation surfaces as a bundle over the Teschmüller space, where each fiber is just a space of holomorphic one form. Okay? And just to illustrate what are the branch points in this language, so the branch points of order n, they correspond to the points, like the vertices of my polygons that have a big angle around them. So for example, this point, if I look around it, it will have a very big angle, angle of, well, you can 6 pi probably. And this will tell me that this point here is a branch point of order 2. And in the language of holomorphic one form, it corresponds to the fact that my holomorphic one form has a 0 of order n. Okay? Okay, good. So first of all, if I want my space of translation surfaces to be non-empty, I need to have that the sum of ni is 2g minus 2. So that's just the Gauss-Bonnet theorem, right? Because we have a flat metric with consingularities that basically are where the curvature concentrates. And so we have this, this must be satisfied if we want to say something. So I'm assuming now that this will be the case. And The holonomy of translation surfaces, it has another name, more common name in this context, and it's called the period map. And the period map has a very nice definition in terms of holomorphic one form. So it's a map that is defined as follows. If I take x omega, the holonomy of x omega will just be the homomorphism from the H1 to C, or the pi 1 as you want. That is, to gamma, I associate the integral of omega along gamma. Okay, and these period maps are very important to study translation surfaces. If you extend them a little bit, they give you charts on those H and 1 and K. Okay. And this, yeah. Yeah. Sorry? Oh, okay. Yeah. Oh, yeah. Okay. So I will say just a little bit more then. So no, no, they're not. They are if you add something. So if you change the H1 here by the H1 with the relative homology with respect to the zeros of omega. So basically, you take all those integrals, and you take also some path that join the zeros of omega, and you integrate along those paths. And this will be a local homeomorphism then. I don't know if I have been clear, but basically what I'm saying is that this is not a local homeomorphism. If you fix a homomorphism here, you can deform within this space by keeping constant the image. This is actually a very well-studied deformation of translation surfaces. It's called the isoperiodic deformations. That's clear? Yeah. Okay. Okay. And the nice thing with this point of view is that we can apply some basic complex analysis. And we can look at what are called the Riemann bilinear relations that tells us that the area of the polygon, in my polygon definition, I can compute it as I over 2 the integral of omega bar, right? Because this first equality is really just from the definitions. If you write omega as dz, you can see that it's the case. And now the Riemann bilinear relation tells me that it's the sum of the determinant of the integral of omega over ai and the integral of omega over bi. And the determinant is when I see them as vectors in R2, but if you want, it's just this. And what are the ai and bi? They are a symplectic basis of my first homology group. Okay, so just as in the picture, a basis where the intersection is 1, like this. Okay, so that's really from complex analysis. And what is very nice in this formula is that you see that the area, which is some geometric information, is only computed by looking at the holonomy, right? This, what I have on the right-hand side, only depends on the period. So that's what I have written here. The area is a function of the holonomy. And the function is this one. To a representation, I associate this function, the sum of the determinant of kai, kbi. Okay, so in particular, if I want a representation to be a holonomy, well, it better have a positive v, right? If I have a chi like this, and I want it to be a holonomy, well, v of chi must be positive because it's an area. And that's almost the only obstruction meaning that the representation is the holonomy of a translation surface in H and 1 and K, if and only if V of K is positive, and an extra condition, which is that V of K is bigger than the maximum of Ni plus 1 times the volume of C over lambda, if lambda, that is the image of K, is a lattice. Okay, so either the image is not a lattice and we have just the first, or the image is a lattice and we have a bit more. Okay? Let me, so I have explained why the first condition is necessary. Let me just tell you why the second is also necessary. So say I have chi whose image is a lattice, and I have a geometric structure with holonomy chi. Then I can look at the developing map from the universal cover into C, and I can map C to C over lambda. And since, because of the equivariance property, this map, the developing map, passes to the quotient to a map from S to C over lambda. And this map is a branch cover. And actually, V of chi will be the degree of this map times the volume of C over lambda. And the degree must be at least Na plus 1 because F is locally Z to the Ni plus 1. Okay, so this theorem is generalizing an old theorem of Haupt from 1920 and has been also proven independently by Bainbridge, Johnson, Judge, and Park at the same time as me. And do you have questions of the statement before I tell you how to prove it? No? Okay, so I'm going to tell you how that works, how you can prove such a thing. And okay, so let's go. Just some ideas. So imagine you're given a chi and you want to find a translation surface whose holonomy is chi. Well, we are also going to do a two-step proof. And the first step is following ideas of Misha Kapovich. And yeah. So what we're looking at is a mapping class group, which is a group of orientation preserving homeomorphism to isotopy. And this group acts on translation surfaces, right? Because if you have a translation surface, you can just pre-compose the charts and yeah, you haven't changed much when you get a new translation surface. And the question is, how does it change your holonomy? And it changes the holonomy as you would expect, because the mapping class group also acts on the character variety by pre-composing the representation. And actually, it acts as an index 2 subgroup of the outer automorphism of the pi1 by precomposition. And these two actions are equivariant with respect to the holonomy. The holonomy of f x omega is f applied to the holonomy of x omega. So what I'm trying to say here is that the set we're trying to characterize is invariant under the action of the mapping class group. Yeah. So that's one fact. And another fact that I'm not explaining, but is that it's true, is that this set that we're trying to characterize is open. And the consequence of those two facts is that if you have a chi infinity in the closure of the orbit of chi, then that is a holonomy, then chi is also a holonomy. Right? Because here, imagine that I have a chi infinity that is a holonomy. Well, since it's open, I have all this red neighborhood that is composed of holonomies. And well, in the orbit of chi, I find someone that is in this neighborhood because it's in the closure and it's invariant, so chi is also a holonomy. So what we want to understand is the closure of the orbits of the mapping class group action on the representation. So we want to study these dynamics, and this is so studying the dynamics of the mapping class group of on the representation of the H1. And it's also the same thing as studying, this action is actually the action of the symplectic group of H1 on the representation of H1. Or if we fix a basis, maybe it's even simpler. It's just the symplectic group integral that acts on C to the 2G. Okay, so this action is far from being transitive, of course, because it will preserve the function V that we have seen before. And the function V can be, in this context of, in this language of C to the 2G is just the standard symplectic form evaluated in the real part and the imaginary part of K. Okay? And now the nice, this is really the observation of Misha Kapovich, is that if you look at the level set of this function V, so you look at V minus 1 of V0, well, the full symplectic group SP2G of R acts on it, and it acts transitively. And the stabilizer of a point is SP2G minus 2. So what we're saying is that this space, this level set, is a homogeneous space on which we're studying the action of a group generated by unipotent elements. So what we can do is that we can use Ratner theorems that are general theorems of dynamics on homogeneous spaces. And we can get a complete understanding of the orbit closures for this action. I will not tell you exactly how that goes. What I want to tell you just is a corollary of this classification is that basically you can reduce the proof to the case where chi is any given representation whose volume is determined, is fixed, and whose image is a given lattice. Because in the closure of your orbit, you will find such a chi. Yeah. Okay. So we are really reduced to a very small number of cases. I mean, just one case here. And now the second step is to provide explicit construction of translation surface of given holonomy. And so imagine, I will show you how that works on an example, but you will see that you could do it in general. So suppose that you are given a chi whose image is Z of I, and you want to construct a translation surface of given volume with those branching orders, 1, 2, 3. What you can do is the following. You can first create a torus like that. Okay, I create a torus. And here I put V of chi, so it has the volume that I want, right? I have 1 times V of chi. But it has no branch point. So I have to create some branch points. And what I want to do is create first a branch point of order 1. So what I'm going to do is just cut my surface here with the distance here between the two that is 1, and glue them together. Like if I arrive to the plus here, I come out here. Okay, so this creates a handle on my torus, and the angle here around this point is 4 pi. Okay, because this point is identified with this point. So I have created a branch point of order 1. But I have also created I have created actually 2 branch points of order 1. So I'm not really happy because I wanted my second branch point to be of order 2. But it's not a problem. I can still continue and just do another cut and glue on my surface like that, right? And so those 3 points here are identified, and I have a branch point of order 2. So I'm happy I have a branch point of order 1, one of order 2, But I have another one here that is of order 1. And I'm not really happy. And I don't want to continue because it will never stop. But it's not a problem. What I can do is just cut like this instead of continuing. And okay, so I cut like this and I identify my sides like that. And this will identify my 4 points here and create a point of order 3. Okay. And now I'm happy. I have constructed my translation surface with the volume V of chi and with the good branch point. So, and by the first step, I knew that I needed only to do it for one surface to know that it's always possible. But maybe what you can wonder is where do I see the condition of my theorem on this picture? And the condition of the theorem is that to be able to construct to do this construction, I needed my first rectangle to be big enough. Okay, so I can find. I mean, I can say that chi is a holonomy if v of chi is big enough to put this sort of pattern in my rectangle. Okay. Okay, so now I have answered to the question of the translation surfaces, so I can go back to projective structures. So if you have questions, time. No. Okay. Okay, so for general complex projective structures, we can do the same, basically the same in more complicated. So that's why I spend so much time explaining this easier case. It's because the ideas are almost the same, but just more technical. So it's again a proof in 2 steps where at first we study the mapping class group action on the character variety and try to understand as much as possible the orbit closures. And then we reduce the proof to a finite number of representations and we construct explicitly projective structures with the given holonomy. Okay. So for example, a particular case of the things you want to prove to study the action of the mapping class group is the action of the mapping class group on elementary representations or on the most elementary as possible representations. So the ones that have finite image, we can here completely classify the orbits. So if you have a finite group of PSL2 of C, you can really understand the orbits of the action of the mapping class group on the representations into this group. And there are actually only 1 or 2 orbits depending on what is your finite group. So if your group is cyclic, you have only 1 orbit. If it's dihedral with odd number of points, you have 1 orbit. And in the other cases that are those, you have 2 orbits. And this was surprisingly not that easy to prove. It was combinatoric, so I had some efforts. And this is just, we have a general theorem of Dunfield and Thurston that tells us that this space of orbits under the action of the mapping class group of representation in finite group is in bijection with the second homology group of your finite group. But this is only true when the genus of your surface is big enough. And there is no control on the genus you need to have this theorem. So if you want a theorem that works in any genus, you have to work. And I think there is still no, like if you were to change H for an arbitrary group, there is no control on the genus you would need for this bijection to hold. Okay. And the second step is explicit constructions that are kind of the same as the one I showed you before. Okay. And so we get the following theorem, which is that a representation is the holonomy of a complex projective structures with branch points n1 and k, if and only if it satisfies the conditions, the six following conditions. So there are six, and they are kind of heavy, so I will not insist on them, but I will still show them so that you can see that it's really explicit. But it's not complicated, it's just long. So for example, the first one is that the parity of the sum of the ni tells you if your representation lifts or not to SL2. And the second is that if your representation is elementary, then the sum of the ni must be big enough. This is just because of the Gauss-Bonnet theorem. And okay, here they are. So, I don't know if I want to read them or not. So maybe I will just say a little bit. Like if your image is finite, then you have a condition that comes from Riemann Hurwitz. Because if you're, say you have a trivial holonomy, having a trivial holonomy is the same as being a branch cover of the Riemann sphere. And so here you have Riemann Hurwitz that tells you some restriction. And if you have finite holonomy, you can go to a finite cover and have a trivial holonomy. So you have this condition that comes from Riemann Hurwitz, and you have also two conditions that are extremely similar to the one I told you about translation surfaces. They are actually the same. If the sum of the ni is 2g minus 2 and you are into the affine group, then you have restrictions that really are the same as the one before. And finally, there is a condition that surprised me in the end, which I have no conceptual explanation for why it's here. It's just I wasn't able to do it, and at some point, I remarked that by some sort of stupid arguments, you cannot do it. But there is some weird thing happening in genus 2. You cannot have what you would expect. I mean, there is an extra condition that is weird, I would say. Okay. Okay, I think I have said what I wanted. So thank you